Okay, it's good to see most of you back. Just because we had like in the break, we had a little discussion about like the data and why we do like peak picking and centroiding and again feature finding and things like that. That all sounds kind of redundant. And that's why I thought I just open up one of the raw data files just to show you, so you don't have to replicate this. So I selected the same two samples from the raw data file that was acquired by the Orbitrap instrument, and then the centroided MZmel file that we processed through MS Convert, right? And that's all what happened. And if we open both and click at one point, I can open the spectrum of both, and you can see how the black one is actually the profile mode spectrum in the raw file, and the blue one is the weighted center of this profile peak. Yeah, so we use the vendor algorithm. Don't know how it works, but it's just using like calculating the centered weight. And of course, because we can detect so many ions at the same time in this mass analyzer, we have this now for like all of those signals. Yeah, so if I zoom in at any spot, we should see that there is like multiple signals, and we can even see that sometimes we're going to end up with something like that because we have very complex data, and it was able to split those and made two signals out of it. And of course, like if they move closer together, you might also not have two signals here. Or if we set the resolution not high enough, we might not resolve it perfectly. But so just that you know, most of the tools that are available out there don't use profile data. So we usually import either one, but then we do centroiding. We do have only one MZ for each signal. So we have like one centroid mass spectrum. And then of course, across the time range, we try to find the same signal and connect them to like a time series. And that's what Stefan is going to do now with you. So, yeah.
Yeah.
I wouldn't do it. I think it's good that we have like this one tool that most people use, and it's kind of standardized. And then there is also like a raw data file parser, like thermal raw data file parser. It's like a different one that you could use, and it's actually the one that we internally use to parse raw data files. Like we don't want to maintain like the whole connection to every like format. So, yeah. And also sharing data with collaborators, I would always share centroid data because no one looks at profile mode data. No one. Like in theory, it's nice, but like I haven't seen anyone do that actually. So and it's just less error prone because I had some people send me results and it was profile mode, and they did GMPS and did like get no networks, no matches, nothing, and we're like, what is happening? And we're like, yeah, you have profile mode data and ran a workflow that's not good.
I already report like a centroid mode, which is much easier for me because then I don't have big data.
Yeah, I mean, with the repositories, you can have big data, just push it there, make it public, and then they have to deal with the big data. But yeah.
Any more questions or yeah?
I'm so sorry. One thing. How can we overlay the Chromatograms?
Yeah, so usually when you just, I'll just go through the whole process again. So when we double click on any file, we just get like the window for one raw data file. And if we want to look at multiple chromatograms at one time, we can update, or like we can select the checkbox up here next to the raw data overview in a tab. And when this is checked, it will automatically update the chromatogram and the spectra in here to the current selection in the main window. And for example, now I can just select like one file, but I can also, with like holding control on Windows, I can select multiple files and then navigate through here and look at those files.
And is this relative intensity?
This
No,
is
this
the,
is yeah, ion intensity that the machine gives you. So it will be different for different machines. It's just like whatever the vendor says it is, we take it. Yeah. Okay, so Robin has already shown you this slide earlier, and now I'm just gonna like yeah, tell you what the next steps are in our processing. So we will need to go from the raw data, which so from the raw data, which is just like a bunch of spectra. So at every retention time, we record one mass spectrum across the whole mass range. We will centroid that data, which has already been done by MS Convert. And now in MZmine, we need to build extract ion chromatograms, which is basically yeah, looking at the intensity of one mass to charge ratio along the whole retention time. These chromatograms will later be split into individual features, is what we call them. Some people call them peaks. We like to call them features in MZmine. And afterwards, if we have multiple samples, we can yeah, align the individual features of multiple samples together. So we have like one big table that yeah, we want to go to with the processing. So to do this, in MZmine, so we have all our files imported. For now, I will deselect the updating here because it will yeah, sometimes update in the background and cause processing that we don't want at the moment. So the first step is the mass detection. Before the break, we ran a really simple mass detection on MS1 and MS2. And usually the noise levels, so yeah, the spectral noise we have in the background of our mass spectra is way different for MS1 and MS2 spectra. If we, for example, look at an MS1 scan here, for just one file. Oops. So I opened a simple MS1 scan, and when we want to determine the noise level, what we usually do is yeah, look across the chromatogram and select some individual scans. And most of the time, you will find a distribution like this. So you have in the front, you have like some yeah, signals that we yeah, want to process later on, and we also have like a lot of signals at the same intensity. And this is most likely due to yeah, instrumental noise. It can be from the detector, it can be like neutral molecules hitting it if you have a top instrument or so, or electronical noise in the Orbitrap. So here, for example, for the MS1, we can see like this noise at the level of 1 E5, which is basically like 100,000 whatever units the instrument gives. And it's always good to look at multiple points in your chromatogram. So for example, at this point, it could be like 100,000. And then if I go to the front here, it's a bit lower. It would be like 40,000. Then back here, it's yeah, again, around like 100,000. And this is only MS level 1. So if we use the same like the same noise level for MS2 later on, we will most likely filter out yeah, a lot of meaningful signals that we don't want to filter out. So it's important to remember that we sometimes in the processing need individual settings for MS1 and MS2 processing. So as Robin already showed you before, we have this table down here, and in that table we can select individual scans. And if I select an MS2 scan now, so in the MSN column, I go to something that has a 2 written here. So it's the yeah, second MS level, and we have a precursor ion selected. And we can see if it was 100,000 right here, that we would basically filter out everything. So we would have an empty MS2 spectra after our mass detection, which is what we don't want at all. And this is probably not a good example. Let's go to this one or so. Yeah. So here we have yeah, our precursor ion. We have some more intense signals, and we also have like yeah, some kind of static noise down here. And when we determined a noise level for MS1 and MS2, we have to apply this mass detection step to all our raw data files. And it's important that you that the noise depends on your instrument settings. So if we determine the noise level for this type of data from this instrument, from this lab, with this HPLC method now, it can be totally different in your lab. For example, the Orbitraps always give like intensities in the range of 10 to the 8. 12 instruments most likely give you intensities to 10 to the 5 or something. It's just important to understand that the settings are different, and each data set needs to be addressed individually. So you can't develop a batch mode or like a whole processing pipeline for one instrument and then one by one transfer it to the other. So when we apply that mass detection, we go to raw data methods, mass detection, and mass detection again. And before we had the scans set to nothing. So the scan filter just said, okay, we apply this settings to all scans. Now we only want to apply the mass detection to the MS1 in the first step, and afterwards we will run a second mass detection on the MS level 2, so we can apply different parameters for that, or like different noise levels, and thereby get the most of our MS1 and MS2 information. So now I went to the mass detection dialog, and here I went to the scans and I clicked set filters, which gives me this dialog. Everybody got here? Yeah, okay. Then I enter MS level 1 here, and then just press OK, and it should update the scan selection over here. Yeah, I can go back. So I went to raw data methods, then mass detection, and here also mass detection. Okay. Okay. So in this dialog, now it deleted the parameters because I said cancel. So in this dialog, I press for the scan filter. I press the set filter option because I only want to apply this module right now to the MS1 scans. And I don't currently care about the polarity. For example, on Orbitrap instruments, if you do like polarity switching, so acquire one scan in positive and one scan in negative mode, you can also use different noise levels for positive and negative ion mode. But this data is only positive ion mode, so we don't have to, for example, care about polarity or something else. And then we have to select the mass detector. Since we have centroid data, we select the centroided mass detector. And to apply the individual settings, so the noise level is always set in the mass detector itself. So we also need to press setup over here, and we get this dialog. And in the dialog, we can enter the noise level. And we said that the noise level was about like 100,000 counts for the MS1 spectrum. This parameter down here, to detect isotopes below noise level, has like some very specific applications. Usually, you don't need this parameter, so I would just leave it unchecked, and you don't need to press setup or anything. So don't worry about this parameter. And when we set the noise level, we can press OK. And then on the top here, it's really important that we apply the mass detection to all raw data files currently in MZmine. So by default, always the as selected in main window is selected, which would mean that currently it would only apply the mass detection to this single file. But if I want to apply to all files, then I have to select all. So the more convenient way is to just say, okay, I want to apply to all raw data files. It tells me, okay, we have 13 raw data files currently, and we want to apply the mass detection there. Any questions so far? Then we just run the mass detection for MS1. And for the MS2 level, we will also set a mass detection. So to determine the noise level there, I would probably say, let's filter out these really low intense signals over here. So let's take like 2000. and yeah, that we get like meaningful MS2 spectra. So again, we go to raw data methods, mass detection, and mass detection. And now we need to change the scan filter to MS level 2. And then we need to also update the noise level that we want to set for the MS2 scans. So here we go from 100,000 to 2E3, which is basically just like 2,000. No, 20,000. And then we also apply the mass detection to all raw data files again, and press OK, and it also processes it, and it should be fine now. Sometimes it's you can have later on the processing, when you forget the mass detection MS level 2, you get some weird issues. For example, no MS2 scans associated with your features. That's then probably due to forgetting the MS2 mass detection. Yeah.
Is there somewhere like a history that you know what you have done to your data?
Great question.
Yes.
In MZmine3, we added that, and we added it properly, or more like better than in MZmine2. And you can, if you select a raw data file, you can right-click it, and then go to Show File Summary. And if I click on Show File Summary, it will open this dialog for me, and it will say, okay, we have imported the data. We then once applied mass detection to a file with like this parameters. Sorry, I'm probably a bit fast. So over here on the left side, we have like the individual modules or processing steps that we did. So we imported data and we did mass detection 3 times by now. So once before for the MS dialog for the visualizer, and now we did it again for MS1 and MS2 level individually. And if I select processing step here, I can see like the parameters listed on the right that were like applied to the module. And later on, you can also export the whole summary, for example, for your documentation or so. And right now, for example, we can see here, okay, for the mass detection, we ran the mass detection with 100,000 for MS level 1. And later on, we ran the mass detection for MS level 2 with 2,000 as a noise level.
And what happens if I want to change a home parameter and I run the mass detection again?
Yeah, if you run the mass detection again, you can either, you can just open the mass detection again, change a parameter, and will override the previous results. In MZmine2, the people that used it, we had multiple mass lists, which was way too confusing, which is why we now have only one mass list, and if you reapply it, it will be used for the future processing. So the latest mass list will be used for the future processing. The previous ones will be discarded.
Yeah. So even if you like have set up like a too high of a noise level, and later you have the final feature table, and you only want to change noise level for MS2, you can even do like all the mass detection on MS2 again, and it's okay. Of course, for MS1, we need all the masses now for the next steps. So you have to do it right in the first place.
Everybody fine with the mass detection? Then the next step would be to build chromatograms for every mass to charge ratio. Because if we look at one spot in the chromatogram here, we can see that we don't only have like 1 or 2 signals, but we actually have like thousands of them at every point in retention time. And we don't want to do that manually and investigate that. So the next thing is that we go to feature detection, because now the actual processing starts. And under LCMS, we have the menu option ADAP Chromatogram Builder. And this module will search for individual masses in the scans and connect the mass traces along the whole retention time. So if I open this module, I will get this parameter dialog. And at first, these parameters can be a bit confusing. So I will go through them right now. So we again have a scan filter, and we only want to build chromatograms from the MS1 data, because in the MS2 data, we don't have our MS1 signals, and it would lead to like just the chromatograms going up and down. So we only look at MS1 data now. We can even, for example, if we know, okay, our column is equilibrating here, and we are flushing our column in the end, we can even set, for example, an attention time range that would just go from like 1 to 17, or 17 minutes, but we don't want to do that now. We just process everything at the moment. So I leave it with just MS level 1. And then this parameter, min group size and number of scans, means that every chromatogram must have at some point 5 consecutive data points. So if we look at a chromatographic shape, so we have the intensity and the retention time on the axis. And for one mass to charge ratio, we look at the chromatographic shape. So this could be a chromatogram. We want 5 consecutive points. So this could be a data point. And we had the discussion yesterday. So this parameter is quite controversial. It really depends on your type of acquisition and your parameters and what you want to do in the end with the data. And I guess Robin and my impression is that you should have at least 5 for a decent peak. If you do heavy MS2, go with 3. If you want to do quantification in the end and want, like, I don't know, statistical good results, then you need way more points on a chromatographic peak for that. So it really depends, like, what you want to do with the data. And so the here we would have this point, this point, this, and this. So they would be 5 consecutive. What can happen in some point, or in some cases, is, for example, that due to some filtering or like some deviation in the mass detection, the shape can look like this. And here we wouldn't have 5 consecutive points, for example, above a certain threshold, and then this trace will be discarded. So this can already later on influence your results. So it's good to check, okay, how stable is my instrument along, like, the whole acquisition. And so we go with 5 now. And then the group intensity threshold means these 5 points that have to be consecutive have to be across a certain minimum intensity. So here we would then want everything to be above this line. And of course, everything isn't. So these 5 consecutive points have to have a minimum intensity of a certain value. And it doesn't really make sense to use the same intensity as we did for the noise level before, because then we could even like discard this parameter. It's always good to have like some statistical like deviation from the actual baseline that you set. So here we would go with 200,000 intensity. And then for the minimum highest intensity, it always makes sense to we don't want to peak to look like this, right? So it should be like, it should have a certain maximum that is like way higher than the baseline that we set before. So I think we're going with 500,000, right? Yeah.
And like those parameters, you're going to see the results in a minute, but are like very dependent on your instrument and also on what you want to do, right? So I have data sets with only 3 data points, and they're totally fine. Like we get very nice molecular networks out of it. It really depends on your study. Yeah.
Then the scan-to-scan accuracy. So the instrument doesn't always, or like due to the centroiding, the peaks can vary a little bit in the mass spectra. And then the scan-to-scan accuracy means how far these peaks or the centroids are allowed to vary in between scans. For Orbitrap instruments, you can like use probably really low values. They are like really accurate, and they are also really precise between scans and really stable. And for TOF instruments, the resolution is a bit lower, so we can also use higher tolerances there later on. So when I, for example, process TOF data, I go to like 0.005 and 15 ppm or so. And then for Orbitrap data, usually I go with 0.02 and 10 ppm. And what's important about this parameter is you might wonder, okay, why do we have to set two different values here? Because the ppm difference is a relative value, right? So if you have a ppm difference of for a mass of 5,000 or so, the absolute difference relative to the 5,000 is way bigger than the absolute difference for a mass of 150. So we decided that it's better to use an absolute value and a relative value at the same time. And MZmine will always default to the bigger value for the certain mass. So for example, at 150 MZ, this value will probably be bigger than tolerance of 10 ppm. And even for lower values, so I know in MS2 spectra, you might like get some really small fragments. It's probably better to use like, small, like an actual value here. You can set it to 0, but then you're destroying the whole purpose of using two tolerances. Yeah.
So it's going to be very precise on like the lower mass range then, with just 10 ppm.
Okay. And here we again set it to all raw data files, or depends on your machine. If your machine isn't that powerful, you can process some files individually. Now, at least on this machine here, we can process all the files. I guess if you have like, I don't know, 8 gigs of RAM or so, it should be fine, right?
It should be fine with most laptops here.
Yeah.
So like, you should just try.
Yeah, just try. Otherwise, we just restart it. And the suffix is basically just a name for later on. And when we apply this, and run the modules, we can see the progress down here at the bottom. And then nothing happened over here, but here on the top in the feature lists tab, we have a lot of new lists, which now contain our individual chromatograms for the individual mass to charge ratios. And to visualize this, you can double click on any file or any list, and it will open the feature table over here. And this feature table in the beginning has a lot of columns. And the great thing is that you can visualize what kind, or you can adapt what kind of information you want to see. Because currently we don't have an annotation. We don't really care about the intensity range or so. So when we want to adapt that, you can click on the small plus here at the top. I hope you can see my mouse. And then we can deselect a bunch of stuff. So currently I would probably deselect everything except like intensity, area, and
It's enough just deselecting the manual.
Yeah, let's just deselect the manual annotation.
Because later on, we're going to show you some annotation modules in MZmine. And of course, the manual annotation is already there because maybe you want to type in some comments and maybe you know what you're looking at. So you can type in those manual annotations, but there's also like more convenient ways to do that automatically. So we can get rid of that. But overall, I think it's important that everyone has now the chromatogram lists, like the feature lists, and is able to open that, right? For at least one file.
Is it still processing for you, or? Ah. Yeah.
Can you show me the list again? What we selected?
For the here. So this is totally personal preference. You can select and deselect what you want. The information will still be there in the background. And like now I just wanted to see the MZ, the H, and the area. And if I want, I can also sort in the columns here. And here, for example, we could then see, okay, the 288 is our most intense signal. And with this retention time at this mass to charge ratio and this feature height.
And it's quite nice that in the table you already have interactive graph. So you can already see the shape of the chromatogram, so the time series. And it's also interactive. So you can like zoom in, you look into the results, and this is going to be for every individual step. and that can help you to also optimize the parameters.
Yeah. Everybody got so far? And one thing that is important for the further processing now is we can already see here for the 288 and for the next most intense peak at the 361 that we have two or more even chromatographic features for one chromatogram, and which will be probably different compounds. So to later on annotate these features and process them properly, we need to split these chromatograms into individual steps, which is also shown here in the PowerPoint. So we want to go from the extracted ion chromatograms to the deconvoluted or now resolved features. Everybody fine? Yeah, okay. Then
close the
I will close the feature table now, and then I can go to feature detection and chromatogram resolving. And for this step, we have a bunch of different algorithms. Our recommendation usually is to use the local minimum resolver or the ADAP resolver for this workshop, and because it's like kind of intuitive or way more intuitive than the other, and then the ADAP resolver, we will use the local minimum resolver, and it's also really fast. So if you have huge data sets, you should probably go with this resolver. So, and we already mentioned that MZmine gives you like intermediate results and also previews during your whole processing. And for this processing step, the previews are really, really important. So before we do anything else, we can, at the bottom here, select the show preview checkbox. And I will just maximize this as well. And we will get like two charts here on the side. And the charts tell us, okay, select a noisy and a good EIC. And to do that, at the bottom here, we have a drop-down menu where we select one feature list. And I will just select anyone or any feature list here. And then MZmine already does like some default parameter or like some default selection, what it thinks is a good and a noisy extracted ion chromatogram. And the selection basically just looks at the ratio of the maximum height to the total area. Because, for example, for this feature or for this chromatogram at the top here, you have the height is not so high, but you have a huge area because it spans across the whole retention time range. So this is selected as like a example bad chromatogram, and the one here at the bottom is selected as a good chromatogram. And to actually like now split the features or the chromatograms into individual features, we need to adapt the parameters here on the side. And I think the problem is that we already have like some values in here. So I will just like type something before we start to optimize it. Because sometimes you can get like crappy results if the parameters are not set correctly. So because this is such an important step, we will go through any or every parameter now. And we start with the chromatographic threshold. So this parameter is sometimes a bit confusing. What it does is you give it a percentage. And this, what it does with the percentage is it looks at all individual data points. So every data point in the chromatogram here, and it selects only it will discard the highest or the lowest 10% of data points currently. The thing is, with actual good chromatographic features, we have like the whole retention time range, so from minute 0 to minute 17, and only, let's say, 5% of those data points are actually meaningful. So we can discard all the other values which are 0 or like really, really low, and only look at the most, like the 10% highest ones. So if we alter this parameter here from 10%, let's go just 50 first. It should already update the preview, and we can see this was shrunk a bit, and we it was shrunk, but we still have like a feature recognized in this forest of something. So we increase it even more. And to 85%, for example, we can also go a bit higher. And see what happens if we put this value to a really, really high percentage. And then we also start to lose, or we also start to not recognize signals at the bottom. So it's always a trade-off. And yeah, so if we go to 89% here, this feature down here is lost. If we go, sorry, to 98%, if we go down to 85, for example, we recognize multiple features here at the bottom. And we still don't recognize anything at the top, which is good because that's what we want. Yeah?
How do you see it's changing? Is it the colors?
Yeah, so the colors at the bottom here, they will they show you what is currently recognized as a good chromatographic feature. And if I increase it to 98, we lose like the first one here. And we definitely see, okay, that there is something, so we want to keep that information. And we also don't want to, have something over on the top here. So if we would go like too low to
1 as a top to edge.
Sorry?
Top to edge 1.
Oh yeah, top to edge 1 and 1.2. Yeah. You can see the parameters influence themselves a bit. So if we have like really unfit parameters for our data set, then we will end up with a bunch of garbage. And this, for example, is totally not what we want in the end with the processing. We want, ideally, you can never, or sometimes you can't tune it perfectly. Ideally, we want nothing to be recognized at the top and like 3 or 4 features to be recognized at the bottom. Yeah.
So like the parameter minimum ratio to top edge, like we set now to 1, that change completely everything.
Yes.
Yeah.
I will come to that parameter later on. It's just for visualization now that with crap parameters, you end up with crap results. Yeah. Yeah. So what you, for example, have here, this is probably some stuff that is stuck in the acetonitrile because it goes up with the gradient and goes down with the gradient in the end. And if you run the same acetonitrile, you probably have the same contaminations, and you can have like starting point for the optimization. You should always like verify that the parameters that you used previously work for new data sets. But if you have like your chromatographic setup and you always run the same HPLC method with the same solvents, you have a starting point, and you can optimize from there, check, okay, is it fine, or do I get garbage out? And then if you get garbage, then you should look into the data and check, okay, where is something going wrong?
So if you have the same acquisition method and the same gradient length, you know, it's mostly about how wide are your features, and then also like how many data points do I have on the feature. Of course, if there's like plentiful, you can raise some of the noise thresholds and some of the shape constraints of the features. But if you always run a similar method, those parameters are always going to be similar. So I don't waste much time there. It's pretty simple to adjust it like a little bit and then you're off to go. And those parameters you can actually understand, like all of them actually have a meaning. So some other tools or some other algorithms are not that easy. So.
No. For example, in other softwares, you give it parameters in the beginning, and then you get results out. Here, you give it parameters for each step, and you see how the parameters influence each processing step. So you know where something goes wrong when your results are weird in some way. So let's go up to some more meaningful value again here. So for 85%, we were able to mostly remove some of the chromatographic noise as recognized as features. And to remove the remaining parts over here, we still have some other parameters that we can tune and to remove that. So the minimum search range means that, okay, I will go through the chromatogram with a certain amount of step size. And if in that step size we find a local minimum, then this is a potential feature. because yeah, and this is a potential feature. Most of the time, it's good to go with something like the full width half maximum of your chromatographic setup, or this is a good starting point. And yeah, here, or a parameter or a value that works most of the time for yeah, HPLC or RP-HPLC methods is like 0.05 minutes. And then to see the difference that this parameter made, we can change it back to 0.01. And down here at the bottom, we see that these features here are not recognized from start to end, but they are like already like cut off on the way down, but yeah, it doesn't go back to the actual value. So if we increase the step size now, we can see that they actually end where they end and they start where they should start. Then the minimum relative height is a parameter we usually don't really use, and we just leave it at 0 because you can have a really intense and a really low intense signal for some mass to charge ratios. What is the better filtering option is to go with a minimum absolute height. And here we would recommend to go with the minimum height that you already also set in the chromatogram building step. So there we said it was 500,000. So the minimum absolute height in the ADAP chromatogram builder for a chromatogram to be recognized as a or like as an actual chromatogram was 500,000, and that's the same that yeah, we recommend here. And now for the peak top to edge ratio. So the top to edge ratio means, okay, what is the ratio between the maximum highest intensity point of a chromatographic peak? So for example, on the top here, and the edge is yeah, the intensity at in the valley between two peaks or when it ends. So here the ratio for the green signal between the yeah, 3E8 and 5E7 has to be greater than yeah, 1.2. And the thing is that with 1.2, it's really, really low. So yeah, that's why we recognize signals in the top chromatogram here. If we now increase the top to edge ratio, for example, to a value of 2, then we should, yeah, we lose the signals here at the top. They are not recognized anymore because they are invalid now with our current parameters, and we can filter out these noisy up and down yeah, signals. Yeah. Any questions so far? Yeah.
Take the left or right side of the
Both.
Yeah.
Yeah, both sides. And that's also sometimes, as we already discussed, you detect a signal and it's like rising, right? And then the mass spectrometer starts to maybe do like top 3, top 5 MS2 scans. So the distance between the MS1 data points gets larger. And so sometimes you have like very sharp edge on the one side and the front, and then like a little bit of tailing. It's not like noticeable, but it's like still like a little bit of tailing. So you have to be careful with this if you have very little data points. But yeah, it's one of the best filters, I would say.
Yeah, you said that for a good PIC you need 3 peaks. I can't find any that has 3 peaks, so maybe I did something wrong with filtering.
Wait, you mean 3 data points? Or?
So comparing the noisy to the good.
Yeah.
Oh, a good thing is you can just go through like the feature list on the bottom where Steffen selected the feature list. So if you click on it, no, just on the feature list.
Yeah, yeah.
You can just change and go through some, because the blank, for example, shouldn't have that many like complex chromatograms, but then some of the other files might have like a nice like multiple peak shape. If you don't find that, maybe it's a contamination in our file or something, but you can also go through the visual features when you sort them there. And of course, you can visualize the feature table at like the complete chromatograms, go through try to find something that's meaningful. It's good if it's like a contaminant, actually, like because then you will always find them in every run, you know, and you can optimize. But like those like closely eluting features are like the ones that we want to see.
Do you want to check it out?
Yeah.
Yeah. And then we have like an additional 2 filter variables. We can also limit the maximum and minimum width of a chromatographic peak. So for example, if we want to exclude some really short signals or exclude some really long signals, we can also like limit it here. And it's another way of filtering, for example, these signals here at the top. So if we reduce the retention time range, we can say, okay, any valid feature in the end should have a maximum width of 1 minute or so. And what you have to remember, or what you have to pay attention to, is sometimes you have tailing in your chromatographic peaks. So here for the blue one, you can see that the tails are, or it fades out a bit. And sometimes the feature recognition would go all the way to the end here, and thereby you filter out a valid peak that just has a bit of tailing, maybe because you set the retention time range too short. So yeah, every parameter can have an influence. I know it's a lot. That's a lot of parameters, but they all kind of make sense, and it's all like a good consideration to know what the parameters are, what they influence, and how they influence the results in the end. Yeah. So for example, if you have like a really high intense internal standard that just has tailing, and you don't find the internal standard in the end in your feature list, this might be an option where you filtered it out. Yeah.
Can you also change the integration? When you say integrations, like don't integrate peak like longer than X minutes?
That's what I just thought. It's because this parameter is like very finicky. Like I don't actually use it that much. Like I usually, and that's what I also want to say. Those parameters depend on the data set, but for most data sets, you can use the same like sort of parameters to begin with. I usually use like a very wide maximum for the range, and then I use the minimum number of data points, which is more important for the lower range, because then I don't have to calculate like how long is actually like 5 data points, like how many minutes is that actually. So I just set like 0 minutes as the minimum, but then 5 data points. So that's restricted. And then it's mostly actually the top to edge, which is mostly your like how many MS1 data points do I have, and the local minimum search window. Yeah, so the minimum search range RT. So that's like, those are the parameters that I optimize. Yeah, like the window and the top to edge. The rest, I have my defaults that work. If you do something where you have a lot of isomers, so a lot of peaks with the same mass to charge ratio and just like across the whole thing, or you do GCMS, where you typically reserve like have the same fragment masses. Yeah, if you do GC with electron impact, you generate the same fragments for so many different compounds, right? Like all the lipids going to have some like the same fragments. You're going to see a bunch of features coming up all across the chromatogram. So you can't just say like, oh, I'm going to discard 85%. But for LCMS, that's not really the case. So it's usually one specific range where you have some mass to charge ratios, and then you can discard 85% and don't lose anything.
Yeah. Then, since we have our parameters set now, we can again go to all feature lists. And one important, one thing is, should we keep it?
Yeah.
Okay. One thing is that we have this original feature list parameter, and you will find it in a bunch of different modules. So right now we have our chromatograms, which are in these feature lists that we currently have, and every processing step in MZmine will create a new feature list. And for optimizing your parameters, it's always good to keep the previous feature list, because then if you did something wrong, you can go back to the previous feature list, change the parameters, and apply it again. If you remove them all the time, you would have to redo the whole processing that you did before. And we recommend, if you run large sample batches, to put it on remove. For now, we keep it on keep, and then apply it to all feature lists and press OK. And now it's already done. And we should have new feature lists with the suffix resolve. Is that the case for everybody?
And we're not going to go like show those feature lists, but usually you can now look into those feature lists and kind of confirm that it worked. But it's usually good to do that downstream once you do the alignment, because we want to now like get all the feature lists into one list, right? And it's just good to keep the track record, and you can always go back and track down some issues that we might have had. Everyone got there, right? Yes. Wait. Yeah.
There's another module that is smoothing. I would like to know when will you use smoothing before the
So if you look at those feature shapes, they don't have like a lot of like going up and down. It's also, especially if you have more MS1 data points, you know, the spray stability in your mass spectrometer might be influenced by your like the speed, like the flow speed, you know. And then this might actually influence the chromatography. It goes like up and down. It's good to do smoothing. Sometimes also to reduce the noise. It might also help with smoothing. But if you don't see any hint that your data needs it, I would just leave it out, do it first, and then come back to it once you feel like, oh, there's like some drops.
The next step in the processing would be to de-isotope our feature list, because right now every isotopic pattern, or every molecule due to its isotopic pattern, has multiple features that represented in the feature list. So for example, here we can see the 254 and the 255 in the feature list. They elute at the same retention time, and they have the same chromatographic shape. So right now we would have a lot of redundancy in our feature lists, and we want to remove that redundancy by de-isotoping our feature list. And to do that, we can go to feature list methods and isotopes and isotope filter. So on the top, feature list methods, isotopes, and isotope filter. Isotope grouper. Yeah, we renamed that module for when changing from MZmine2 to MZmine3, because it would explain the name better. Or at least we hope so, that it explains better what it does. So what we can do now is set up MZ tolerances, RT tolerances, and some further stuff. But a problem, or like something to note right now, is that we currently have multiple feature lists per raw data file. So if we would now select all feature lists, we would apply the processing to 26 instead of just 13 files. And an easy way to circumvent that is if we say a feature list name pattern. So a pattern is something that appears in all the feature lists that we want to process. So I go to feature lists and feature list name pattern. And then I go to the select button here on the side. And in that select button, we can type in a pattern. And in a pattern, you always, we can see that all the feature lists that have been produced in the last step are called resolved in the end. So our pattern would now be resolved, but the beginning of the name of the feature list is always different. And to introduce something that applies to everything and resolved in the end, we can just place a star or an asterisk, I think it's called in English, and replace an asterisk and resolved, and then press OK. And now we can see that it currently selects 13 feature lists again, which is what we currently want. Okay.
Can you show the history of feature lists as you did for the mass detection?
We do in the end.
Afterwards.
Yeah. I think we also need to speed up a little bit. But you have time. You have time for it.
How long do you need for the data set?
Not so much. Yeah.
So,
time for this one.
Any questions so far? Yeah, I'll open it again. So we go to feature list methods on the top. Then now we work with the isotope. So we go to the isotope menu and then the 13C isotope filter. And here again, for the feature lists, we now want to process all the names, all the feature lists that have resolved in the name. So we go to feature list name pattern and then go on select. And in the name pattern, they are all called resolved. And to address for the difference in the beginning of the name of the feature list, we can put an asterisk, which is basically like a wildcard. It can be anything. And now we have 13 feature lists selected. And as Robin mentioned before, we have always these MZ tolerance parameters. And the MZ tolerance here applies to how much the expected 13C isotope difference. So the difference of 1.003 differs from the actual measured value. And since it's the same instrument, it's averaged across a whole feature. And since it's averaged, we can set this tolerance lower than what we did before for the chromatogram building. So here for our data set, a value of 0.001 and 3 ppm should be totally fine, because we don't want to remove any signals that are not an isotope pattern by mistake. It's better to have like some redundancy than to filter out more than you need to. And since the isotopic pattern should elute with the same shape and at the same retention time, the retention time tolerance can also be really, really low for like one acquisition. And since we're not working with IO mobility data, we don't need to do anything here. Yeah.
What if you have internal standards carbon 13? Would that be effective?
Yes. And to not make that affect your analysis, you can check the monotonic shape here. So then it would expect the isotope signals to decrease with rising mass to charge ratio. And
So the question was if like 13C labeled standards would be like interfered by this one. I mean, first of all, it depends on how many carbons are actually exchanged, right? So how much do you shift the mass actually from the original one? For small molecules, as Stefan said, you usually have a monotonic shape. So the first signal, the highest one, even for singly charged, like the first one is the highest one, and then we have +1, +2, and it just fades away. And of course, for proteins and bigger macromolecules, it's way different. There you're going to have more like a huge shape. Of course, if you have only one 13C that is exchanged, that might get like pretty tricky. And then I would just maybe not do this step. This is only to clean up the feature list. So we don't want to lose anything meaningful here. So we set the filters very narrow. Yeah. So it doesn't matter if we don't detect all the 13C isotopes here. We just want to remove everything that's evident, just redundancy.
So I'm working with chlorinated and brominated compounds most often. And like what they have different isotope pattern, and they're really different. So can we work with those as well? Like, or
this filter only applies to the difference of 13 or like carbon isotopic shifts. If you want to later on scrunch up all the isotope patterns of like chlorinated and brominated compounds, for example, we have a different module for that also recognizes them. And in the back, we also have something lying around that will also remove the chlorinated features from the feature list. Reach out to me if you want. currently they will be left in the feature list unless you uncheck the monotonic shape and raise the MZ tolerance so that the chlorinated or brominated peaks would also be in that tolerance.
Yeah. But like overall, there's also a problem for everyone who does not understand the problem of having like a complex isotope pattern. There's like, let's say bromine, bromide, or chlorine, right? And we then, we have different isotope signals, and at least for like those ones, we have +2. And +2 might actually get like higher or the same intensity than the original one. Or maybe even if we have multiple fluorine, it also like shifts the pattern completely. And then you also have to ask yourself, which signal is selected for MS2 fragmentation? So it's not very clear. Sometimes it's both. So it might also be good to keep that in your data set so that you have the MS2 spectra of like both maybe. And then in the libraries, you also sometimes only find +2 and not the like monoisotopic as like the reference. So
then we can also specify maximum charge states, because the difference of the 13C signals will depend on the charge of the molecule. So for singly charged molecules, the difference will be 1.003. For doubly charged molecules, it will be 0.50015. So in MZmine will look for those differences, and if it finds something, it will remove it. And we can limit these differences to a maximum charge state. So for example, for small molecules in metabolomics, for example, we recommend like a value of 2, unless you know, okay, I have like some compounds with multiple protonation or deprotonation sites, then you can also, of course, like raise that value. Yeah. Later on, the representative isotope just means which isotope will be kept in the feature list, which is the most intense one most of the time. And we can also select that we never want to remove any feature that has an MS2 associated with it, which is what Robin just mentioned. If you have like a weird isotopic pattern due to some halogenated compounds or like high molecular masses, you will definitely want to keep that MS2 information. And here we also select that we want to keep the original feature list, and then we can apply the processing. Then the next step, we now removed we removed the redundancy that we had in our original feature list, and which doesn't mean that every feature now has an isotope pattern, because we might have filtered out with our filtering parameters, which were quite strict, I would say, and we might have filtered out some isotopic features. What we can now do is for our features that remain, we can go back into the raw data and or in the scan data and look at the individual scans to find, okay, can we find an isotopic pattern for this molecule? And if we can find that, then still add it to our feature list. And for that, we go to feature list methods, isotopes, and isotope pattern finder. And in the isotope pattern finder, we basically have the same parameters. We can tell it which elements we want to look for. Right now, we can, for example, even add. So for example, if you work with chlorinated and brominated compounds, we could even add the chlorine and the bromine. And we can, for example, also like remove the sulfur if we don't expect sulfur or so. And then we can just press OK. And then this MZ tolerance is the MZ tolerance within one single scan. So this module will check, okay, when is my signal the most intense along the retention time? And it will take that retention time and look, okay, at this scan, do I have an isotope pattern for chlorine, bromine, oxygen, nitrogen, carbon, whatever we want to look for. Yeah.
This has nothing to do with like iron or the ionized with ammonia or like sodium. Is this now neglected if we don't put it into the chemical formula?
You mean if
That's going to be like later downstream. So it's only, and it might be confusing for some people in the beginning, but this is mostly for annotation later on. You want to annotate your compounds based on all the information that you can get. And we get some information from the MS1, which is the isotope pattern, and that we might have multiple different ions from the same compound. And then, of course, the MS2s. And the first step was only to filter out evident like 13C isotope features from the list. But that's very limited, only like to the feature list. And now we just try to, like we do with the MS2 spectrum, we try to have a feature attached with the MS2 spectrum, and now we attach the MS1 isotope pattern to the feature. So that later on when we export to Sirius and to other tools, or like use it in MZmine, that we have all this information. Yeah, it's an optional step and you don't have to do it. We just decided to show it at least for people who, of course, do like chlorine and like some special isotopes. This is very important. Yes.
Yeah, so the 13 carbon only removes, it's only filter, only removes the feature, but doesn't like relate it to the.
It does relate it also. So the filter filters out. That's why we renamed it to filter. Yeah, it removes information and it's very strict and very like we don't want to remove too much, right? And the finder is very open. It might also find stuff that's not the isotope pattern, but it finds some stuff that is in the range of being relevant for that information. So it just goes in the data very openly, just looking for stuff to connect. Yeah.
Yeah. And since we're here looking at the same scan, any mass differences should apply and to the monoisotopic and the isotopic features as well. So we can like lower these tolerances a bit, and then go with the same maximum charge state. We again have to set the featureless name pattern, and which is now de-isotoped in the end. So we can again asterisk and call it de-isotoped, and we can directly see, okay, did it work? It works if we have like 13, at least for this data set, yeah, files detected, and then we can press OK again. Sorry? Yeah. Two zeros. Did I use 3? Oops.
And you can do it again.
You can do it again. It will overwrite the previous results. So we can do it like this. And we have still the name pattern. And this step didn't create a new feature list. It just associated new information with that one. So we can leave it at, yeah, the featureless name pattern and run it again. Asterisk, de-isotoped. Wait, I'll show you again. So most of the modules in MZmine, when they create a new feature list, they just append a suffix to the name of the previous feature list. So you can see here, we started with chromatograms, then it was called Chromatograms Resolved, and then it was called Chromatograms Resolved the isotope. And now we can just work with the de-isotoped.
In the end, we're also going to end up pushing everything in a batch mode, and that's going to be way more convenient.
Yeah.
This is only like to show you like where the modules are actually located and so on. But then later on we do it in batch mode, and then it's only like a few clicks to set everything up, run it, and have the results. But
yeah. Yeah, and now we have our individual samples pre-processed. And now we want to put everything together to, yeah, not look at 13 individual tables, but look at one table that contains all the relevant information. So we can again go to featureless methods and alignment and join aligner. And this aligner will yeah, look at intensity. No, sorry, it will look at mass to charge ratios and retention times. If you have ion mobility data, we'll always also look at the mobility values. But for our purposes, we just align on mass to charge ratio and retention time. So the MZ tolerance here, again, a different one, will compare the a variation of two features for the same compound in different acquisitions, so in different samples. So since it's averaged and the Orbitrap mass spectrometer is like, yeah, really stable, we can go with 0.01, 2 zeros, and 5 ppm mass differences. And as a retention time tolerance, as we can see in the, or as we saw already in the beginning, I'll just show it to you. You don't have to do it right now. If I just select, let's select the replicates, we can see that the retention time in the individual replicates was really, really stable and didn't shift much. So we can use a kind of low retention time tolerance to align features from one sample to the other sample. So we can go with, like, for example, 0.06. And then we have these two parameters, which are called weight for mass to charge ratio and a weight for retention time. So what they do is they basically score the difference between two individual samples for mass to charge and retention time. And we can always say, okay, mass to charge ratio is more important than retention time. And some values that we recommend is going like with 3 and 1 for mass to charge and retention time respectively. And the mobility weight, I think it should have a value, but it doesn't affect us. It just needs to have like some value in there. So doesn't do anything. And we again keep all the original feature lists and the parameters down here. If you want to do like some more complex alignment, you can use them, but for now they are not relevant for us. So the last thing we need to do is again select the correct feature lists, and they are, I guess, now called De-Isotope. Yeah. So again, we select the name pattern. And with asterisk De-Isotope, and we can press OK afterwards. Everybody fine so far? Stuck anywhere? Okay.
Oh. What? 900?
What?
70 megabytes, I have 450. No, the 13 was 60 megabytes, and there was one file like
Nice.
All right.
Okay.
That's gonna be nice for the end report. Like track down why those files are so different.
Then
We have to talk about it.
we can start aligning the features onto each other.
you click OK already, right?
Yeah, I clicked OK, and it's already done, which was really fast.
Yeah.
Usually it might take a little bit longer and not finish instantly, but if we now open that feature list, we can see that our chromatograms here yeah.
If we have a bigger retention time sheet, how we adjust variables?
For the alignment, you mean?
Yes.
You can, or you mean how to find out the retention time shift and how to adapt it adequately? Yes. Yeah. Like what you can do, or like what's the easiest way is to go into the raw data overview, and as I did here, click through like some signals that you know are the same signal in the different files, and then check, okay, how much do they actually shift? And the tolerance should then be like in the range, so set in a way that it accommodates the shift. So for example, if you had a shift of from 6.14 to 6.4, I would adapt the tolerance to 0.2, for example. And put it higher. Okay. Yeah, then you have to raise the tolerance. Yeah. 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 So the question, or like the note was, sometimes the retention time shifts aren't constant through the whole chromatographic run. You can either use higher tolerances, or for that case, we also have a different alignment module, which is the Renzac aligner, which will basically put like a fit through some standard features across multiple samples and shift the retention times non-linearly to do a better alignment. Yeah.
Then we did some steps, and then I'm like, okay, I don't like it. I want to try the start of the beginning.
Yeah. So the question was, if we later find out that we messed up somewhere, can we, like, how to proceed then? So for example, if we find out, okay, in the resolving we messed up, what we have to do is go back to chromatograms here and adapt the resolving, and then also adapt the steps that come afterwards. One thing that will help you with that is the summary. I will get to that later. Anybody else needs help currently? Okay.